I'm looking for the best method from Sklearn's cross-decomposition module to uncover the relationship between gene expression data, X, and clinical measurements, Y. I want to find a way to reduce the dimensions of both datasets while keeping the important connections between them. Think of it like finding the most important patterns shared by two large, complex datasets. PLS regression is a great tool for finding linear relationships between X and Y. It aims to predict Y from X, or vice versa, while maximizing their covariance, which means finding how much they change together. It's a good fit because I want to find how gene expression influences clinical measurements. It's a solid choice. PLS canonical is like a fancier version of PLS regression. It maximizes the correlations between the hidden factors, latent variables, extracted from X and Y. It excels at finding relationships and reducing dimensions when dealing with paired datasets, which exactly matches my problem. This is a great one too. CCA, or canonical correlation analysis, directly finds linear combinations of variables in X and Y that are maximally correlated. That's perfect for revealing hidden connections between gene expression and clinical measurements. It's a top choice for this task. I like this one a lot. Kernel PCA is for dimensionality reduction on a single dataset. I have two datasets, X and Y. So this method doesn't address my goal of finding a relationship between them. It doesn't consider the connection between X and Y, so I'll skip this one. This is not the right choice. I need to choose the methods that can effectively analyze the relationship and reduce dimensions for paired datasets X and Y. This means I am selecting those that work best to maximize covariance or correlation between my two datasets. I'm looking at a dataset, X, representing gene expression. It's high-dimensional, meaning it has lots of variables, genes. Think of it like a spreadsheet with many columns representing gene activity levels. Similarly, dataset Y contains clinical measurements, also high-dimensional, which probably means many different patient characteristics are recorded. This could include things like age, disease stage, blood pressure, and many more. We again have many columns in the spreadsheet format, showing measurements for each patient. The goal is to find a relationship between these two datasets, X and Y. That's like finding out if the levels of certain genes, X, are linked to specific clinical outcomes, Y. Because there are so many variables, we want to reduce the dimensionality. This is a bit like creating a summary of the data. Instead of using all the original gene expression and clinical measures, I will try to use a smaller number of key features that represent as much information as possible. PLS regression is a technique that attempts to predict Y from X, or vice versa, while maximizing the covariance between them. It's great for finding linear relationships between datasets and it helps reduce their dimensionality while keeping their core relationship. PLS canonical is like an upgraded version of PLS regression. Instead of focusing solely on prediction, it aims to maximize correlation between the core components extracted from X and Y. This helps reveal the relationships even better. Canonical correlation analysis, CCA, directly searches for linear combinations of variables in X and Y that show the highest correlation. It's a powerful technique designed to uncover relationships between high-dimensional paired datasets, perfectly fitting our need. Kernel PCA is only for dimensionality reduction with a single dataset. It can't find relationships between two separate datasets like X and Y, because it doesn't consider the connection between them. It's unsuitable for this problem. I'm representing the data containing the gene expression levels. Think of it as a bunch of numbers showing how active each gene is in a sample. This is one of the two datasets we're comparing. This is the other dataset. It contains clinical information about the same samples used in the gene expression dataset. This could be anything like patient age, disease status, or treatment response. We're trying to see how these measurements relate to gene activity. It's like detective work, using one set of clues, genes, to solve a mystery, clinical outcomes. We need to pick the right tool from the Sklearn library to find hidden links between the gene expression and the clinical data. It needs to handle lots of data points and show us how the data relate to each other in a simplified way. PLS stands for partial least squares. This method finds the relationships between X, genes, and Y, clinical measurements, focusing on prediction. Can we predict Y based on X? It's a great way to look at how one dataset can be used to understand the other. This is like a fancier version of PLS. Instead of just prediction, it tries to find the strongest relationships between the underlying factors driving both datasets. It aims to find the hidden connections more directly. Think of it as finding the core similarities between the two sets of numbers. CCA means canonical correlation analysis. This one directly looks for the strongest linear relationships between two datasets, focusing on the correlation between them. It shows how the main aspects of X and Y change together. It's very good for our problem. Kernel PCA, Principal Component Analysis, is a technique for reducing the number of dimensions, variables, in a single dataset. This won't work for our two datasets because it doesn't look at how X and Y relate to each other. It only works on one dataset at a time. I'm using Sklearn, a popular Python library for machine learning. Specifically, I'll be using its cross-decomposition module, which offers tools for analyzing the relationship between two datasets. Think of it as a toolbox with special techniques to uncover how two different sets of information are linked. I have two datasets. One contains gene expression levels, which I'll call X. The other holds clinical measurements, which I'll call Y. My goal is to discover if these two are somehow related. This dataset contains measurements of gene activity levels. Each row might represent a different patient, and each column a different gene. Think of it as a list showing how active each gene is in each person. This dataset contains various clinical information about patients. That could be things like age, weight, disease severity, or treatment response. This data is what I'm trying to link to gene expression. Both X and Y have many dimensions, lots of genes and clinical measurements. That makes it hard to analyze. I want to find low-dimensional representations of the data. This is like creating a smaller, simpler picture which shows the main relationships without all the detail. This is one technique from Sklearn. PLS stands for partial least squares. It helps me find relationships between X and Y and predict one from the other. It's good at finding linear relationships that can be plotted as a straight line. Similar to PLS regression, but this version focuses on maximizing the correlation between the sets of data. It's really good for finding the strongest links between the gene expression and clinical information. CCA stands for canonical correlation analysis. It's another method to find strong relationships between X and Y by finding combinations of the variables that have the highest correlation. It's specifically designed for this kind of paired data problem. Kernel PCA, Principal Component Analysis, is a great technique but works only on a single dataset, not on two related sets like we have here. It can't tell us how X and Y relate to each other. I'm looking for methods that excel at finding relationships between paired, high-dimensional datasets. The goal is to simplify the data while maintaining the strength of the relationship between X and Y. This requires techniques designed for multivariate analysis and dimensionality reduction, specifically focusing on paired datasets. Think of it like finding the hidden connection between two complex puzzles. PLS regression is perfect for finding linear relationships between X and Y, aiming to predict Y using X, or vice versa. It directly addresses maximizing covariance, making it a great choice. It's like finding the best linear fit between two sets of points. PLS canonical is a variation of PLS, but it's focused on maximizing correlations between the hidden structures, latent variables, extracted from X and Y. It's excellent at uncovering relationships and reducing dimensions in paired datasets. Think of it as finding the most correlated hidden patterns within both datasets. CCA directly searches for linear combinations of variables within X and Y that have the highest possible correlation. This is precisely what we need. Imagine finding the best matched linear summaries of the two complex datasets. Kernel PCA is a dimensionality reduction technique, but it only works with one dataset at a time. It can't directly find relationships between X and Y because it doesn't consider their covariance. This method is only good for simplifying a single dataset, not finding relationships between two. I'm looking for a method from Sklearn's cross-decomposition module that can handle high-dimensional data like gene expression, X, and clinical measurements, y. I want to find a relationship between them, reduce their dimensions, and keep the important information showing how they relate. The best method will maximize the covariance, how much they change together. We have two datasets. X contains gene expression levels, and Y contains clinical measurements. Both datasets have many variables, high-dimensional. Both datasets, X and Y, have a large number of variables. This is why we need a method that can handle high dimensionality effectively. This is repeated for emphasis. Dealing with high-dimensional data is a key aspect of this problem, and selecting the right technique is very important. PLS regression is a good option. It finds linear relationships between X and Y and predicts one from the other, maximizing their covariance. PLS canonical is another great candidate. It's like PLS regression, but it focuses on maximizing correlations between the underlying factors extracted from both datasets. Canonical correlation analysis, CCA, directly aims to find the linear combinations of variables in X and Y that have the highest possible correlation. It's excellent for finding relationships between paired datasets. Kernel PCA is not suitable. It's designed for dimensionality reduction of a single dataset, not for finding relationships between two datasets like X and Y. I'm looking for a method from Sklearn's cross-decomposition module that can handle high-dimensional data like gene expression and clinical measurements. I needed to find the relationship between these two datasets and simplify them into lower dimensions while maintaining the strongest possible connection between them. This means finding the method that best preserves the covariance, the measure of how much the two datasets change together. PLS regression, partial least squares regression, is a good choice here. I can use it to find linear relationships between gene expression and clinical measurements, aiming to predict one from the other while maximizing covariance. It's designed to work well with high-dimensional data and excels at extracting relevant information. PLS canonical, partial least squares canonical, is another strong contender. It's a variation of PLS, but it focuses on maximizing the correlation between the simplified representations of gene expression and clinical measurements. This aligns perfectly with the goal of finding the strongest relationship and reducing dimensionality. CCA, canonical correlation analysis, directly tackles the problem of finding linear combinations of variables in gene expression and clinical measurements with the highest possible correlation. This method is designed to find the strongest links between the two datasets and is ideal for dimensionality reduction in this context. Kernel PCA, kernel principal component analysis, is a dimensionality reduction technique, but it's only designed to work with one dataset at a time. I can't use it to find relationships between two datasets like gene expression and clinical measurements. It doesn't consider the covariance between X and Y, therefore, it is not appropriate for this problem.